So we're really grateful to have a really outstanding panel today. It's titled Optical Revolution in the Data Center and the Cloud. So a couple of the speakers that have just spoken are on the panel, and I'd like to introduce the new people. So Alexis Bjorlin is Senior Vice President and General Manager of the Optical Systems Division of Broadcom. And again, that's all of Avago. So we're very glad to have Alexis here. Secondly, Gordon Keeler. So Gordon is at DARPA, MTO. Before that, he was at Sandia, but he runs, hundreds of millions of dollars of programs. In particular, Blum's program has a number of different photonic foundries that he has under contract. So that's really going to change silicon photonics in a major way. Kaushik Patel, he's Director of Engineering, Silicon Photonics Development at Cisco. And as you know, they've recently acquired several companies, silicon photonics companies. And so he's led their 100 gigabit product and the most recent 100 gigabit PAM4 product. So he's been a real key person in silicon photonics for a long time. And then Clint, who's a professor of electrical engineering at UCSB. And he leads a large effort, particularly in coherent and in VCSELs before that. And you heard from Catherine about the collaboration they have together. So with that, let's start. Maybe we'll go through the order that's listed on the panel and get a few comments, and then we'll take questions. So Alexis, do you want to start?
Sure. So first off, thanks for inviting me on the panel today. It has been wonderful seeing all the work on co-packaging and interconnects. So to just start out, and with about a minute, I'm leading up Broadcom's Optical System Division. So I came to Broadcom in particular to solve this exact problem. So we named ourselves the Optical System Division because we are taking a system level view. As Catherine mentioned earlier, we need to collaborate and co-design to re-architect the network platform in the same way that the server platform has recently been re-architected. So you'll see the rise of application-specific computing and a re-architecture of servers. I see it as a very similar opportunity for us to re-architect networking, interconnects, and redefine at a system level. It could be, and this is the exact moment that my kids are making noise, but it could be at the global data center footprint, the inter-data center network architecture. We have tremendous partnerships where we're looking at all aspects of that. It's also at a system on a chip level. So the SoC architecture, the partitioning of functions, what's in the electrical domain, what's in the traditional optical chip domain, and in packaging. And then it comes full circle to reliability, serviceability, availability. So how we think about how do we bring out this type of technology that will ultimately provide up to 30% power consumption savings for the network as a whole. That's our goal. When Catherine showed that the network is taking up more and more of the power, our goal here is to try and help find solutions to solve that. So at Broadcom, I'm very lucky to have an awesome team where we have all of the traditional optics, the indium phosphide from Browningsville Bell Labs, the HP VCSELs, but we started a startup right within Broadcom with an incredibly diverse team of silicon photonics designers, CMOS designers, and we're working across Broadcom's platform with our networking, Asics, switch, NICs, application-specific compute Asics. We view what we're building here as a platform not only for the network, but to solve the problems in compute scaling and disaggregated memory at the same time. So where are we today? It's a gnarly engineering problem. This is no joke. One of the most complex things I've ever looked at. And, I very much appreciate Robert's vision. Intel is really driving, had a great demo. We've got a whole ecosystem being created. I think Cisco's, driving down this path too. Also, being fed and, really that collaboration with Microsoft, Facebook, and the other hyperscalers is absolutely critical. But this is a problem that we're going to bring out. I'm in agreement with Robert's statement that there will be absolutely co-packaged optics available at the 25T network at the switch level. Absolutely full production systems at 51T and ubiquitous at 100. So love the discussion on coherent versus direct detect. We think about that as well, but that's kind of my nutshell.
Thanks, Alexis. And I should have mentioned that Alexis ran the Silicon Photonics division at Intel before she went to Broadcom. And obviously, this 25 terabit switch is 50 terabit switch is huge dollar volume for Broadcom. So this is really critical. So next, Gordon Keeler.
Yeah. Hey, everybody. So, right, I'm Gordon Keeler. I'm at DARPA in MTO. I manage most of the photonics and optical microsystem programs that we've got. I've been lucky to work with a whole lot of really good teams. And so I myself don't really do anything, but I get to talk about all the good results that we get. We look, I would say, pretty broadly at applications for optics, and information is sort of one of them. And so that can go into data center and computing, particularly for interconnect. And so John talked about the PIPES program, which has a lot of similarities to the Enlighten program that Mike Haney was talking about previously. We've been going for about a year. We actually have our big program review on Monday. And so that is really being pushed by the challenge of moving data around. It's not just in the data center. It's sort of everywhere. And so it's in DoD applications, it's in compute. And we're looking maybe a little bit farther out than some of the immediate commercial drivers. And so, we're looking at GPU, CPU, FPGA, co-packaging. And in those kinds of applications where you only maybe have a few hundred watts that you can play with for the whole capability, you really do need to push efficiency up or total link power down. And so we're sort of starting at a picojoule, and we're looking at going down 10x for some of the harder technical areas. So John was talking about 100 femtojoules. That's sort of all in everything, including the laser and the electrical signaling. So I think that will, even if we don't quite get there, that'll have a big impact on power dissipation in data center. We also are working with Intel, and so other folks at Intel were able to demonstrate a FPGA Stratix 10 integrated with some optical chiplets. It ties in nicely. I also have a program called CHIPS, which is all about sort of the chiplet ecosystem. And if you think of photonics as being yet another chiplet that you can integrate into these complicated packages, it enables you to do a lot of things. I would say another point is that a lot of our other programs use integrated photonics, but not so much for moving digital bits around. It might be for doing compute, might be doing for quantum compute. There's a lot of microsensor or LiDAR or chip scale clocks or gyros needs that we have. And so we're leveraging smart ideas coming out of integrated photonics. And then often they go back the other way. So, Dan was talking about some of the really quiet laser work that came out of chip scale gyros. Then that can go back into coherent. And so I think there's a huge opportunity space when we kind of look broadly at the applications that you can enable with integrated photonics. So comb lasers, some of the results that John was talking about previously came out of the DODOS program, which is all about doing a self-referenced optical frequency comb on chip for high stability kinds of applications. Once you can do that, then you can, say have a comb source that you could use in DWDM. So, lots of different things. John asked me to talk a little bit about the Lumos program, maybe as my last thing. And Robert made a great case for having lasers and gain on chip. And I think we're going to push on that even harder, and maybe other materials as well. So Lumos just kicked off, and it's really about using the benefits of silicon photonics, meaning manufacturability and high yield and high volume, but bringing some of the materials that we really want to have in the optical world, which is 3.5s, maybe silicon nitride, lithium niobate, and how do you intimately integrate those materials in? So we're doing that in large foundries. We're also doing it with academics and small companies with a bunch of different goals. One of them is to have sort of a broadly accessible capability to create things like neuromorphic computing on chip and so on. But also we're looking at really high power, low noise lasers for RF and microwave kind of applications. And then finally looking out in the visible to enable a lot of the emerging quantum and atomic system applications. So that's really one I'm super excited about. We have a lot of great ideas, and I'm looking forward to see what we get on Lumos. So anyway, that's me. Thanks.
Thank you, Gordon. Kaushik? I think you're muted, Kaushik. I see him there.
Can you hear me now?
Yes. Little echo.
Not sure what's going on.
Are you connected in two ways, Kaushik? Phone and computer?
I just jumped in and muted everybody else for the moment. But
Well, Kaushik's checking. Why don't we move on? Clint Schow, Professor UCSB.
Hi, so I'm Clint. I wasn't quite sure of the format, so I guess I'm supposed to say what I'm working on a little bit and then maybe ask a question or two. Is that?
Sure, well, we'll ask you questions, but you can ask the other panelists questions. Yeah.
So that's fine. I think I definitely appreciate the talks. It was worthwhile seeing all this activity that's going on. So the program that Catherine alluded to that we've been working on, Mike Haney's Enlightened program. There's that echo again. We've been working on trying to bring coherent to data centers for 3-4 years now, and I think the approach is a little different from what we heard this afternoon. So instead of using quiet lasers, we're trying to use, I would say, cheap and dirty lasers and optical phase lock loops to clean them up. And we've made the argument, I think, that we want to use DSP-free techniques for a long time. And so I'd like to spend a second on that one, because I think we're not all on the same page with what that means, DSP-free. So in our case, we've chosen the simplest possible modulation format that we could get, which is QPSK, sort of dipping your toe into the coherent waters. And the reason we did that was if you use QPSK, once you've separated I and Q channels, you're making hard binary decisions. So you use the same electronics for NRZ. And so it's really the most power efficient way to do things. You're not having to sample multiple bits per symbol. And we did this because, again, it was sort of the simplest thing we could possibly do. So in the context of energy efficiency for data centers, I guess I'd like to highlight that as maybe a different approach. There was the question earlier about VCSELs and VCSELs versus silicon photonics. So I'll take another little contrarian view there too. I think if you look at the way data centers are built now, and we heard it, that we have copper in the rack still. And why do we have copper where copper can work? Well, because it can work, and it's the simplest, cheapest thing. So I would say if you're sort of climbing the ladder of interconnects, I would make the case that for things like conventional HPC, where you have 30-meter interconnections, VCSELs are going to win every time. And I appreciate your comment, John, about the number of multimode fibers that you might have to bring to a chip. But fundamentally, bringing a multimode fiber and coupling it to a VCSEL is a much easier problem than coupling a single mode fiber to a PIC. So I think there's going to be different application spaces. And I think that's what's great about these kinds of forums where you see the diverse viewpoints, because one size doesn't fit all. And we're certainly going to have, I think, technologies that win in certain spaces. But I would say the lessons I've learned is that the simpler, the better, especially in terms of power efficiency. As soon as complexity starts driving up, power starts driving up. So on the point of DSP, I guess the two questions I'd like to ask, which I think were common to John and Dan's presentations, are the laser work's incredible. what are the wall plug efficiencies that we can get for these devices? Either the really quiet Fresco lasers or the comb sources, because I see numbers that are impressive on the order of 40 microwatts to generate these lines, but the power per line isn't to where we would need it for a communications link. So I'm wondering, when we sort of look at it from the practical end-to-end standpoint of the link, how good can we do with the wall plug efficiencies? And then the DSP point that I'd like to highlight is, I think when we say DSP, we're lumping in really two different aspects. One of them is, if you're going to use DSP, you have to get the data in the digital domain. And so if you have PAM4 or you have higher order modulation formats with coherent, you have to sample multiple bits per symbol. So you need a linear front end, and then you need an ADC, an analog to digital converter. Then you go into the DSP world. And again, this is my understanding, not being a complete expert, so I'd love to hear answers. I think DSP, the back-end digital logic, has scaled very well, because fundamentally that is a digital operation, and we've continued to scale it even though we may see the end of Moore's law. A to D converters scale too, but not nearly as well. And I think Dan Blumenthal and I were on an email thread with Chris Cole within the last couple of weeks, where Chris is making the argument, which I think is supported by some heavy hitters in the ADC world, like Professor Boris Merman at Stanford, that adding one bit of resolution to your ADC is a 4x hit in power. So the scaling properties of going to very complicated modulation formats, if you care about power efficiency, I don't see those as much. If you care about capacity and how much you can put in a duplex fiber link, it makes complete sense. But so those are the aspects I guess I'd like to hear a little bit more detail on, is that how efficient can we get these lasers, and that DSP issue. Is it really DSP that we don't want to do, or is it we have to avoid having to do heavy ADC conversion?
I'd love to answer that. I will in just a second. Let's see if Kaushik, have you solved your audio problems?
I'm going to unmute. Can you hear me now?
Yes.
Oh,
no echo. That's
fantastic.
great. Why don't you say
Hey,
a couple
John,
comments, and we'll address Clint's questions.
Okay. So John, I've decided that I'm going to get you a good deal on WebEx. I spend all my time on WebEx, and I'm relatively new to Zoom. Anyway, thanks for inviting me to the panel. I think, as you mentioned earlier, Cisco has made some significant investments in silicon photonics, starting with the Lightwire investment, followed by the Luxtera investment in 2018, and most recently, the Acacia investment, which is still pending. And one of the key reasons why these investments have been made by Cisco is to drive silicon photonics-based optical interconnect products into the data center. And the key careabouts in the data center around cost, power, and overall performance are the key metrics we're trying to achieve with these technology investments. As far as our current products are concerned, we are very focused on 100 gig per lambda products from 500 meters all the way up to 25 kilometer. These are all direct detect products, O-band, uncooled, and CWDM grade. Separately, we have a portfolio of products around 400 gig ZR and coherent that address the data center connectivity market. And as part of this current product deployment, we are very focused on low loss integrated coupling solutions for laser and fiber coupling, highly integrated CMOS electrical and optical ICs with COC flip chip packaging, and a fully integrated TX and RX all on the photonic chip. And part of this investment is around addressing the kind of the packaging requirements for low cost power and high volume production. In addition to these investments, we have lined up some very significant wafer fab partners, leveraging CMOS cost model to give us the type of cost targets that the data center customers are looking for. So separate from these existing investments, we also have a lot of work going on in advanced development around our key building blocks. Some of you may be aware of this. We have a modulator called the SysCap which is deployed in current generation. We are taking it to the next level of performance. And together with that, we have an integrated germanium detector that we're now advancing to the next level of bandwidth and low loss requirements for all the way up to 200 gig per lambda type of performance. Somebody mentioned earlier around Asics and optics integration. So there's a significant amount of effort underway right now on IP or CPO, where we're moving the E2O and O2E conversion closer to the switching routing ASIC. Separate from these internal investments, we also have some significant university collaborations underway. The first one, John, is with your team around the 3.5 integration into a silicon photonics platform, and then eventually kind of the holy grail, where we expect to be able to get QD lasers integrated into the silicon photonics platform as well. We also have another collaboration underway with Columbia University, Karen Bergman and her team, around energy efficient optical interconnect solutions, all the way from the electrical ICs to the actual optical E2O and O2E conversion element. So I think the key message here is, from a Cisco perspective, we're fully committed to silicon photonics in the data center, and making the appropriate investments to get us into a leadership position in this area. That was it. Thank you, John.
Thank you very much. Maybe I'll very briefly answer Clint's question, then I'll put it back to you guys. So Clint, I mean, your comment is very valid in the sense that we can get 35% wall plug efficiency out of quantum dot lasers. But when you make a mode lock laser, you lose a lot of efficiency. None of them operate at 35%. So 15% is a pretty good answer at the moment, but we're trying, I think we understand how to improve that. And then similarly with the comb generation, the wall plug efficiency, you know, is in 10 sort of percent. The thing we're doing differently on that 3 Hertz line with one I mentioned, we're not using bright solitons, we're using dark solitons. So the light is on for almost the entire period, and then it's off for just a brief time. And that gives you a lot more power per line. So you can get above -5 dBm up to sort of 0 dBm. So again, we're using those things with quantum dot SOAs to get the powers up. And the quantum dot SOAs can be quite efficient, you know, 40% sorts of efficiency. So that's kind of how we're viewing it. But let me put the question to Alexis, because I mean, she did VCSELs as for a PhD thesis, and obviously she has VCSELs as well as silicon photonics at Broadcom. So what's your opinion, Alexis?
Got to unmute. So I believe that the lowest cost, lowest power consumption, and predominantly lowest cost solution will always win. Just to make a note, there are a number of servitor interconnects today that are VCSEL based. If you look at the China cloud service providers, just to provide some context there, there's still a huge amount of multimode fiber. You know, when it comes to considering the cost of coupling to multimode lasers versus our VCSELs versus high density arrays, I mean, I actually think it becomes a wash once you get to a high density array. And you're going to, you know, you could design that for a passive alignment. You could design it for an active alignment. But if you're aligning, you know, 32 channels or 16 channels in one time frame or one, that cost isn't dominating the system level cost. So at a big picture level, you know, I think a lot about where VCSELs can play. I think actually Catherine also spent a lot of time deliberating over this, you know, multiple years ago before making the decision to go single mode in the data centers in the North American hyperscale. So I do think that for when you own the end-to-end link, you could really utilize VCSELs for proprietary interconnects. If you're looking at a scale-up compute system where you're building something such as a supercomputer, but you know, overall, I think just given the bigger topic at hand with data centers, I think silicon photonics is the clear winner, and will achieve the same power consumption and the same cost structure as VCSELs by the time this is launched in either the 25 or the 50 terabit switch system timeframe.
I would just agree with those comments, just to chime in. I think we all have dark VCSEL past, so I had to stick up
Yeah.
a little bit. But no, I mean, I think in our current research in my group, we're doing a little bit with VCSELs still, but the main line is certainly silicon photonics. So very good points.
So John, I guess try to address some of Clint's questions on the energy efficiencies of the lasers that we make. So I just want to say that I think you'll notice that people over the last 5 years had said, why would you ever want a low line with laser? And that certainly was the pushback that we got when we first started publishing our results on a subhertz laser. All the reviewers, a lot of people asked, why would you want a subhertz laser? Well, I think people are starting to understand why you would want a subhertz laser. So the question is, what would you pay to get it? You know, the different application spaces, right? So for this application space, we haven't published this yet, but we are now well under 1 milliwatt thresholds for our Brilliant lasers. So using John's lasers, we can now crank up Brilliant with less than a milliwatt threshold power. Brilliant itself is 100% efficient. In other words, using the gratings, you can get up to 100% conversion efficiency. The question is, how do you get there? We have demonstrated what's called a inhibited cavity that I think that others have figured out recently in our field, where we inhibit S2 of the Brilliant from lasing, so all the energy continues to go into S1. So I think over time, we're going to start to see these really quiet lasers become extremely energy efficient. And the fact that you can now imprint that purity onto a comb and use it as a so-called power supply source for these high capacity systems, it's amortized. So, you know, I just think that it's really important not to rule out anything at this point, especially when you're talking about amortizing really pure sources for high capacity systems. So, you know, I think one should keep an eye out for the wall plug efficiencies of these lasers, ones that John works on, the one that we work on, and I think they're going to keep going down. The other thing that I'd like to say is that, you know, there was a very strong message sent out earlier on about the architecture and the physics going together hand in hand. And I think that the discussion has to head in that direction. If you have new physics, a new operating point on how you do something, and it allows you to build your data center architecture differently, the energy win can be a top down instead. You know, you can talk about doing packet coherent communications with a pure source where you don't need tracking dead time anymore for packets. I mean, so, you know, I think that it's good for us to have open conversations about this ecosystem of an architecture and how you do the business underneath different ways and how they work together to get you an energy efficient solution. And so that, you know, that's what we get really excited about with the Open 2018 project that we have that Mike started on. And I think you had another question about ADCs. I hate to say it, Clint, but you were left out of about 75% of the conversation with Boris. And I'm sorry about that. I didn't realize that you weren't on the thread. I just went back to check. But we're actually seeing gains in ADCs. Using quiet light, we can dial the E knob down significantly. And when you can, most of the hit that you get in ADC energy consumption is because of the E knob penalty that you pay. So, you know, I think there's a lot of work to be done. You have to talk specifically about how you implement an ADC. And we don't think about ADCs as DSPs. So DACs or DAC-free coherent transmitters, which you can make, by the way, ADCs, those we consider that all to be a DSP-free environment. So I just wanted to at least get our language down on the table for what we consider to be DSP-free. And we think there's a lot of room to grow on the ADC.
Thanks, Dan. Well, yeah, you guys can sync up offline. Other questions from panelists or from the audience? We have the heavy hitters. Go ahead. I'll just finish my comment. We have the heavy hitters here. I think Intel and Cisco have, what, 98% of the silicon photonics market today. And Broadcom obviously has a very large fraction of the big switch market. So we have the key players here.
Hey, John.
Hey, Mike, go ahead.
Yeah, it's Mike, sorry. I just wanted to probe a little bit on Clint's comment on the VCSELs and the application space for VCSELs possibly being with the future HPC applications. Isn't it true that there's a trend in HPCs, and I don't know the answer to this, but it seems that there's a trend toward very complex compute nodes. And that would imply to me anyway that the bandwidth to and from those nodes, which consist of multiple CPUs and GPUs, is just going to be driven higher, faster. Now, I could be wrong about that, but I just would like to get your comments on that.
So from my perspective, it is true. So hybrid compute systems, whether it's scale up full on GPU nodes themselves using NVLink or an NVSwitch, can be interconnected. Those can be interconnected in a proprietary manner. And I think that NVIDIA has been pretty vocal and engaged in, I think it might even be POET, some DARPA. So you could see today all of these, and then their acquisition of Mellanox is pretty interesting because Mellanox has been doing all the HPC InfiniBand fabrics that are largely all interconnected with VCSEL-based interconnects today. So when we see these two companies come together, the ability to architect a system at scale, as long as it's less than 100 meters link, you can get up to 100 gigabit per second using a VCSEL-based technology. Now, if you're talking about right now, everything's still interconnected. Like if you have 4 GPUs on a blade, or or on a board, those are still electrically interconnected today because the cost of silicon photonic interconnect is still higher than electrical, even with the complexity of the board material today. But I do see a future where you can have when you think about even more bandwidth to these compute node chips, including the massive increase in memory that's needed. So it becomes, how do you enable a disaggregated cache coherent memory pool associated as well with all of this, with the connected nodes of the compute system? That's where silicon photonics starts to look very interesting.
Thanks.
Just interject a comment to Mike. It's gone the wrong direction, and you can ask Data for the slide, but the US took back the #1 supercomputing slot last year, and it was with a system that had those big, heavily accelerated nodes. But if you looked at the bandwidth coming off those nodes, it's gone the wrong direction. So when you look at bytes per flop, it's just been on a downhill trend. So they're heavily, heavily connected and powerful inside the node, but those nodes don't talk to each other very well. And that problem's only gotten worse if you sort of plot it.
Hidden a lot of the interconnect problem inside the node.
Well, getting it out of the node. So I think within the node, they can still use all those great buses and interconnect the processors and the accelerators. But then when it has to talk off node, it's going through a really, really thin pipe. So you could turn that around and say, well, this is the opportunity. This is the opportunity where silicon photonics could bring that higher bandwidth off the node and make better systems that could solve problems that demanded more interconnection between the nodes.
Yeah, I would maybe just quickly add also, I mean, I think Clint mentioned that the cheapest solution will win, or Alexis mentioned it, but I think what we're seeing in some of these high density nodes is copper just doesn't work anymore because it's just too thick. It just uses up too much space, right? And even on the VCSELs, if you're doing standard pluggable type AOCs, you're just running out of bandwidth in terms of the terabytes of data you need to get to and from some of these nodes, right? And I think that's where we're seeing this integration. And that's where obviously silicon photonics can come into play when you do the co-packaging, right? So I think it's not just the dollars for a link, but it's really like physical constraints and the density of some of these clusters, right? So it's a sheer bandwidth that needs to be supported.
I think this is where I think the folks working on silicon photonics really need to focus on the cost drivers for that interconnect solution, right? Because I think all of these interconnection solutions will quickly migrate to optical solutions if we can get our hands around the cost. And that means coupling, lasers, integration on the electrical IC, integration on the optical IC, and the overall power dissipation of that solution.
Good point. So maybe actually we could hear from the other panelists. What do you see are the big holes? What's your biggest problem that you need solved? So there's certainly a lot of academics on the line, but also just industry-wide. What are the big issues? And So I don't know if we could go around the whole panel. I'd love to hear your opinions.
I think sort of, standardization, obviously, like a consensus on, what the form factors are and so on, obviously are key, aligning all the stakeholders, because we don't want to be going down a hole that, then you need to get out of and do it slightly differently because, it's not quite compatible. So I think, that's to some extent it's limiting some of the progress, I would say, in certain areas, right? So yeah, alignment, and I think that's why some of these initiatives, like in the OCP and or the co-packaged optics collaboration, I think these are really, really helpful. It's at least one point that came to mind. Yeah,
John, if I can just make a quick comment on the kind of form factors, right? So Cisco, obviously, with a bunch of other people, have played a key role in kind of standardizing on the form factors. And that generally has helped the industry drive to a common solution and drive the cost down. But we're quickly approaching a stage where pluggable optics are coming to an end. And the optical I/O is moving into the line card. And that's where the challenges are going to come into play in terms of how do we standardize and how do we make sure we can leverage common foundries, common PDKs, and so on to develop that optical interconnect solution.
Agreed. Agreed. Alexis, what keeps you up at night?
What keeps me up at night is getting the product built. So, I mean, I think a lot, unfortunately, my approach has always been from a very pragmatic perspective, is how do you get a product actually built and ramped? So I think all of these challenges need to be solved. We are using standard interfaces, such as like the SerDes interface on the output of the switch is a standard LR, MR interface, VSR, XSR. So I think that, driving electrical standards and still having the optical standards are very important, but it's too early in the development to clamp down and start talking about form factors. We're changing the form factor, we're changing things every single week. So we're very much in a process, an iterative process to enable the technology and enable a solution that can work. And then, I'm 100% on board that we need to go to open interfaces. But right now, I think we need to find really pragmatic solutions that dramatically reduce the power consumption and that offer disruptive cost value propositions so that, we're actually, all the industry can get behind this and we can build that ecosystem. I don't think we need similar PDKs we all have our own device design libraries. There's not similar PDKs between, all of the different laser foundries, right? But we all have laser output, eye diagrams we have to meet, MSA standards. And I think, we have to really think about that and in order to innovate, you have to put oxygen into the system. And you have to allow for innovation to happen and unique approaches at this early stage. So I think that's one of the challenges is a lot of people talking, I think it's very important that everybody's open and transparent and we share the challenges that we're facing, but at the same time, in order to bring a product out after all the years of innovation on silicon photonics, still we don't have a at volume co-packaged solution. Acacia may be one of the earliest with the co-packaging of the DSP and the silicon photonics. And then, the only person that I think you missed on the silicon photonics side is obviously Inphi, is making a lot of headway there as well. So.
Gordon, you hear from a lot of people things that aren't public. What do you see as the big needs and big problem?
Right. So I'm not supposed to say any of that, or you guys won't tell me anything. So I could say a lot of things, but I would say I agree with what Alexis just said about I think it's useful, at least in my chair here, to make sure you kind of blow off the doors and don't constrain anything because so much is still moving at this point. I'm actually trying to make sure that we're looking at new and emerging markets really hard, because I think that sometimes those are the things that are unexpected, but they, come up out of nowhere, and it's not switch chips or something like that ends up being the main driver 5 years from now. It's something else that dwarfed that market, and then switch chips end up coming along for the ride, right? And so it's I don't know that it's yet consumer electronics or anything like that, but we saw that with VCSELs when VCSELs started to be used for 3D sensing and so on, right? Suddenly, 8 months in, all the VCSELs made for that application dwarfed everything made in history, right? And so I think silicon photonics has that potential, and it could be that it's in co-packaged optics. It could also be that it's in some sensor, time of flight, or LiDAR or something in your phone, or a biosensor that goes in your Apple Watch, or I don't know what it is, right? There's lots of different places that you could see it happening, and trying to get the synergies aligned so that you can ride on those waves, I think, is really important.
Great, thanks. Clint, I'll give you the last word on the panel.
I don't know what to say. I mean, what keeps me up at night is how fast things are moving. I mean, I think especially in research, when you look at how fast the industry is driving and you have to try and stay out in front of it before you get run over, that's sort of what makes me. And then I think the complexity of everything that we've talked about involves multiple moving parts. There's electronics and photonics and packaging and integration. So the scope of the problems to a large degree is expanded, and the time frame to solve them is contracting. Having said that, I wouldn't change anything. It makes it fun, right? It's good to be scared.
I agree. All right. Well, on that note, I'll hand it back to Mark. William Wang is next, and we've heard earlier, machine learning AI is a big driver for this. So, Mark, thank you all the panel. I think you guys did a great job, and I appreciate all your contributions and everyone in that session.
Yeah, what wonderful
Thank you.
stuff. Thank you, everybody.